So this video is for Physics 12. It's the fourth lesson in Chapter 6 for electric circuits. It's the last day that looks exactly like Physics 11. And we're going to take a look at Kirchhoff's circuit laws. And all of this, again, looks exactly like Physics 11. So starting off here with this one circuit, it doesn't have any I's or V's actually in there on the page yet. It's definitely a combination of series and parallel, which we'll go through in a moment. But off the start, I'm just actually going to use just a little FET applet to see what all these various values are for voltages and for current. And off the start, I'm going to take a look at all these current values. So there they are, and I'll show you just how I would do that on the FET applet here in a second. The total current coming out of the battery is 1 amp, and you'll want to pencil these numbers in. Current through, that's how we would say it, through resistor 1 is 0.75 amps. Current through resistor 2 is 0.25 amps. The current through resistor 3 is 1 amp, and then the current through resistor 4 is 0.4 amps, and the current through resistor 5 is 0.6 amps, or what some people might call 600 milliamps. Now, how would you actually come up with those numbers? Well, you could go to your little circuit simulator here, and if you want to check out currents, you're really supposed to actually break the circuit and then some contact. And if over the wire, it tells you how much is flowing through. So the printing's pretty small, but that does say 1 amp here, 2.5 amps, 1 and 0.4 amps. So the notes on the note sheet there. Now we'll put in. Oh, okay. How much we're going to lose of these, and the beginning is 6 volt good wire. Oh, it's a 6 volt drop to go through, and this one as well, a 6 volt drop across that resistor. For this middle resistor, the volt across here is going to be a 12. So those values in. Now, look at the current, sometimes called the junction law. He's a total current has to equal the total current out. So for example, for resistors 1 and 2, when they join back together, the 0.75 amps and the 0.25 amps does indeed make 1 amp. And then as you look at that third resistor splitting into paths 4 and 5, 1 amp does equal 0.4 plus 0.6. Now the voltages, you saw them a second ago on the voltmeters there. We can pencil those in. And they do not all add up to 20. You know, if you go 6 plus 6 plus 2 plus 12 plus 12, you get like 38. That does definitely not equal 20. But that's not what Kirchhoff said would happen with the voltages. He said you have to think about these loops, these little shopping trips where you're spending your money. And he said around any loop, the total voltage gained has to equal the total voltage lost. And with our shopping analogy, that's like saying you go to the bank and get yourself $20. By the time you make your way back to that bank, you will have spent exactly $20. No more, no less. You can't go into debt, and you can't save any of that money. You have to spend it all. So that's the two laws. Now, underneath that, you've got this little thought on, okay, when is it useful? Well, same circuit that we've just been using, but let's propose you're in a situation where you knew these numbers. Maybe you knew that current number 3 was 1 amp, right? If you knew current number 3 was 1 amp, and if you knew that current number 5 was 0.6 amps, you might look at that junction right there and go, oh, at that junction, I know all of that 1 amp in has to be leaving. So there has to be another 0.4 amps leaving. For voltages, it's a little trickier. You have to be thinking about loops. So you have to find a loop where you know every single voltage drop and gain except for one. So in this loop, I see a gain of 20, I see a drop of 6, a drop I don't know, and then a drop of 12. Well, I can account for 18 volts of drop, and this would have to be the rest. That's why V3 would have to be 2. So that's a situation where you would actually be applying these circuit laws to find some useful value for you. Okay, next page here, let's talk about the difference between series circuits and parallel circuits. Here's a nice little series circuit, and I'm going to simulate that one as well, just to try to look and see what's actually going on with the story here. So I've got some resistors that are in a nice little series circuit, and if I check out the current, I find that the current is the same everywhere. 2.5 amps, 2.5 amps, 2.5 amps, always 2.5 amps. But it's quite possible that the voltage drops it's going to depend on these resistance values. That resistor 25 volt, then a drop of 50, and the last 25 indeed add up to the battery voltage of 100. Voltages could be, if they were all the same resistor, then all the same value, then you'd find that the voltages would be the same. But typically the voltages are different and the currents are the same. Now if I take one of the resistors and move it, just maybe it melts and evaporates, so a little cloak. So if it's gone, that totally eliminates the chance for the electricity to flow. Okay, there's no way that happened. So let's go and take a look and see what we can pencil in for our notes here. So for a series circuit, the resistors are all in an electrical line. There are no junctions. That's the key thing. No places for the current to split. All the currents were the same. That's always going to be true for a series circuit. So if you know one current, just already say, hey, I know the current on that next element in the line. Can't be any different. If one of them fails, if it's gone, if it's removed and is not replaced, and you don't just connect the two wires together that form that gap, if you leave that gap open, the circuit definitely stops. The voltage drops are typically different, okay, unless you make all the resistances the same value. When you're calculating total resistance for a series circuit, you do nothing but add them all up. You're just adding up the ohms in that story. That tells me if you were to add another resistor in series, the total resistance always grows. Okay, that's something to keep in mind. The only time you'll get the voltage drops to all be the same is if you make all the resistance values identical. Sometimes we do that in circuits, especially for things like Christmas lights, but generally that's not true. Okay, parallel circuits. That's when the resistors are all side by side. Most importantly, connected with wires, top and bottom. So I'm going to take a look at that circuit here. So here's my parallel circuit. What I can see is electricity is flowing through all of them, and not equally. And you might think, oh yeah, it's close. Actually, there's one in the middle. One's on either end is actually the same flow of current. So it doesn't take every path that it can. When I go to check things like currents, what I'm going to find may be different. So 7 amps on the main wire, 1.5 voltage drop. Parallel 30 volts on that one. So the voltage drops are the same, but the currents are typically different. You can rinse the same distances. If you have a big gap, well, the others can keep going, but here is a very commonly misunderstood issue. Right now, with all three of them running, I have one in grand total to right here. I could go away in just a second. A lot of people think that, oh, well, battery always must send out 7.5 amps. So now the 3.7 amps has to go. Yes, that total current right here has dropped 6. This has at 3. So don't think that the battery always produces the same amount of current. If you change the amount of resistance it experiences, you see a change. So that's up for the resistance by side. They don't have to physically point in the same direction. They have connected with solid wires top and bottom, what we sometimes call a voltage bus. all the voltage drops are going to be the same. This is actually just a consequence of the loop law. It says, well, if you did a little Kirchhoff loop through number 1, next time if you do your loop through number 2, it has to be the same experience. So they have to have exactly the same voltage drop. If one of them fails, the rest can continue, but do expect to see the total current out of the battery diminish. The currents are typically different unless you make all the resistors exactly the same. Now, adding up equivalent resistance for things that are in parallel, you actually have to do this addition of reciprocals. You have to reciprocate each of the R's, then add them up, and then reciprocate back. I think what we in Physics 11 called flip, flip, add, flip. What's really happening there is you're not adding up the ohms. You're adding up the mhos. You're adding up the conductances, right, for that circuit. Now, you could get all the currents to be the same if the resistances were all identical. Sometimes we do make circuits like that. Okay. Now, you've got this handout with this set of combinations here. The first combination is going to take us 5 pictures to get right. It's 48 volts. And then there are 4 resistors, and it's not just series and it's not just parallel. It's some sort of interesting combination of the two. And what I would do is make your plan of attack to first try to find the total resistance. That'll take us like a whole page here. And then we'll find the total current. That'll be easy. And then we can play the game with Kirchhoff's laws and Ohm's law. That goes pretty fast. So I think we did this one in Physics 11. Probably the place to start would be these 2 resistors here. They actually have wires top and bottom, so they're connected in parallel for sure. And what we can do is combine them and just call them a new fictitious replacement equivalent resistor number 5. So number 5 doesn't exist except in our minds, but we can drop it in place of 3 and 4. So I would do a parallel calculation where I would go 60 flipped plus 90 flipped and then flip it back after you've added. And I promise you the final answer should be less than the lowest one you see. It should be less than 60. And when you do, you find that it's actually 36. So we can put that 36 in there instead of the 60 and the 90. Now, where do we go from there? Well, it looks like number 2 and number 5 are connected in a line now with no junction. So we can do a series calculation. So I'm just moving down the page. I'm going to combine them together and call it number 6. Got the 24 and the 36 we just found. That's equivalent to a 60. Resistor 6 doesn't exist except in our minds, but we can drop it in there to replace the other 2. Now those 2 are going to be in parallel. So I can do a parallel calculation, and the final answer is always going to be less than the lowest, so it's less than 40. Yeah, it's 24. We are 1/3 of the way done. We've got the total resistance. Now we're going to go for total current and then finish the game. For total current, I'm going to do Ohm's law globally on the entire circuit. I'm going to take all the voltage that I've got and all the resistance that I've got, and I'm going to exercise Ohm's law, and that says it's going to be 2 amps. Okay, so there's 2 amps coming out of the circuit. Now if you go over to the next page in your handout, let's go back and look at this whole circuit over again, knowing at this point that there are 2 amps leaving the battery. And we're going to see if we can figure out what's going to happen along the way. And you want to be looking for any little Kirchhoff or Ohm's law maneuver that you can do. I can't do Ohm's law at all right now because I don't know any V's or I's. I would need to know like 2 of the 3 things in Ohm's law in order to proceed. But what I could do is look here and go, hey, there's a nice little loop right there. If you gain 48 volts in the battery, one option is to go through number 1 and then go back to the battery, and you have to spend all your money. So that's got to be a 48 volt drop. So I can go and pencil that in. Say, all right, great, I've got 48. But that very moment when I go and drop that in there, I now know 2 of 3 things at that resistor. I know the V and I know the R. So I can go and find the current with Ohm's law. So I'm doing Ohm's law right now just on resistor 1. And if I swing Ohm's law around, it looks like that current's, I don't even swing it around, I just go V over R. I get 1.2 amps. Okay, great. Now what you have to pick up on is this junction up here where you've got 2 amps going in and 1.2 amps went down, straight down through number 1. That means the rest, 0.8, has to continue down this wire, and it will continue right on through resistor 2 until it gets to that junction. So I can say, hey, That current in resistor 2 has to be 0.8 amps, 800 milliamps if you wish. All right, well, as soon as I've done that, I now have two things for resistor 2. I have its resistance and its current, and I can do Ohm's law to figure out the voltage loss there, and it's 19.2 volts. And so I'm going to pencil that into my little diagram. And before I go too much further, I have seen some students look at this voltage here and go, wow, that's confusing. I might have thought it would be 48 because it's just come from the battery and it was a 48 volt battery. Yes, the charge carriers do have 48 volts available to them, but we're talking here about how much are they going to use here at this spot. So they're going to drop out of their 48, 19.2 in resistor number 2. Now, with that idea in mind, if I've spent 19.2 here, let's do a little trip through resistor 3. This voltage 3 has to be enough to get me up to that 48 volt drop. So just thinking about loops, voltage 3 has to be 28.8, and I can put that into my picture. Now, most people actually would say, hey, resistors are in parallel here, 3 and 4. Voltage 4 has to be 28.8, and that is absolutely right. Absolutely right. But I'm going to show you kind of a back way that you can get there. What if you figured out the current in number 3 first with Ohm's law? Right, it ends up being 480 milliamps, 0.48 amps. You can put that in. Now, you could just say, well, I know the voltage on number 4 is 28.8. You're right. Or you could say, hey, there's a junction. 0.8 amps just split. 0.48 went one way. The rest, 0.32, must have gone through number 4. And that works too. And then you can do Ohm's law to find voltage 4. But no surprise, it's 28.8. So that's the deal. Look around and see if you can find places that are in series and parallel. Work your way until you combine them back to a total resistance where you can find the total current. And then you just have to look for little places where you can do Ohm's law or where you can do the current law, the current junction law, or the voltage loop law. There's only one scenario, it's our last example here, where you can get into a little bit of trouble, and that's where you sometimes have to work with groups. So this circuit here doesn't look too complicated. I've got one parallel group in series with another parallel group. I can get started pretty quickly to get this thing rolling. For the first parallel grouping, a 54 and a 27, I'm expecting the answer to be less than the lowest, less than 27, and it certainly is. That group, I'm going to call it 5, it's 18 ohms. Easy stuff. And then I do the same thing, and I'm going to call 3 and 4 together group 6. And I do that flip, flip, add, flip thing, and I find out that the resistance equivalent there is 32. So I now have one resistor that's 18 in series with a 32, and pretty quickly I get to the series addition of 50 ohms. And so far, I'm making good ground in my table here. I can sketch in my total resistance, no problem at all. That's 50 ohms, and I can even find the total current, 0.18 amps coming out of the battery. But then I'm absolutely stuck. I don't know how much of that 0.18 amps goes up or down in this branch. It's not going to be equal because the resistances aren't equal. And I don't know any of the voltage drops. I only know that by the time you go all the way around, it adds to 9. So sometimes you have to stay thinking about groups, like that group 5 and group 6 that we were talking about. So think about it as kind of yellow blob, blue blob. It's now a big series circuit, and all of that 0.18 amps flows right on through those blobs. So it's kind of like this. Just pencil in here a little bit. Right, you've got this current that's flowing right on through there like that, 0.18 amps. So now I can go and do Ohm's law for those groups, for the entire yellow blob or the entire blue blob. For the yellow blob, 0.18 amps flows through it, and the yellow blob is 18 ohms. And I can do Ohm's law to find the voltage drop there. And the same thing for the blue. And here's what I find. For that group 5, the voltage drop on that yellow group is 3.24 volts. Do not cut that in half. I know there are 2 resistors there, but that's the voltage from the beginning to the end of that yellow blob. So you can just go and put in 3.24 volts for both. Now, the blue blob, group 6, It has 0.18 amps, but it's 32 ohms, and the entire blue group as a group has a drop of 5.76. Don't cut it in half for voltage 3 and for voltage 4 when you're wondering, okay, what do I put in here and what do I put in there? Just go with that full value of 5.76. Okay, we can drop it into the table. Now at this point, it's actually pretty easy finding I1, I2, I3, and I4. I don't even think it's very interesting. It's not the most interesting part of this example. That was how we could find these voltages using groups. But if you really, really want to see it, yes, you could go and now do Ohm's law and find out all of these individual currents. It's not the most exciting part of the story, but yes, it does actually work. So sometimes you have to work with the groups, not the whole circuit, not a specific resistor, but kind of stranded somewhere in between.